would like to tell you the entire story of the universe in an hour, and a bit about how we learned about it, and my personal part of this process, and where we're going from here. And the title slide here says, from the Big Bang and on, etc., to the discovery of alien life. And so we haven't exactly found it yet, but I think it's possible in the next few decades. And so I want to outline at the very end how we are hoping to find out about that. So there are many, many mysteries. But first I'll start with how did I get into science. And so here is a picture of the place where I grew up. It's an experimental dairy research station in northern New Jersey. And I like to say that's a site of early nerds in Sussex County, New Jersey. Of course, nerds have been around here for thousands of years, but we didn't always have that honorary title. So anyway, this is a good place to grow up if you want to see the sky, because it's dark at night and clear, and there's a lot of time to think, because if you're not actually doing farming, you have time. So I read a lot of books. And my parents took me to the museum in New York City to see the planetarium show and the fossils and the bones and the exhibits about volcanoes. And I was just really, really excited about science. But it was at that time, a long time ago, people hardly knew anything by comparison to what we know now. So I got to get in at the beginning of a tremendous wave of scientific research, and it's been exciting ever since. So I want to share some of that excitement with you all about what it is people have been up to for the last many decades. So now we have a picture. This is a picture of the entire universe as seen from the inside, made with a recent satellite mission called WMAP. And so we have now a picture which we call an image of the baby universe. And so I will tell you a little bit about what it means as we go along. But this is what we think of as the beginning. And so if we understand things right, we should be able to take computers and make calculations and say, well, all these little speckles that you see in here will eventually grow up to be something. And so what we think is that these are maps of the dense regions in the early universe, and the dense regions are going to grow up to be galaxies. So we have a story which illustrates here in this chart that says tiny things form first, little tiny galaxies. Galaxies are hundreds of billions of stars nowadays, but in the beginning maybe there were just a few stars together. So little galaxies form, then they bump into each other, make bigger galaxies, and they bump into each other and make bigger and bigger galaxies, pretty much like a small streams flowing down the hillside will merge to form a giant river. So this is our idea about how galaxies like our own Milky Way were formed, but it's an idea, and we can't exactly prove it just yet. So on the other hand, we can look at collisions happening between galaxies. Here's an amazing one. This galaxy has clearly taken a piece of the other galaxy, and they've sort of wrapped it around in curls around this one. So this one is evidence that galaxies have been colliding. And if we really know how this works, we should be able to simulate it in a computer as well. But just for now, it's one of those mysteries, because we don't honestly know how it works. And what you see is not necessarily what you get either. There's a lot of stuff that's unseen in a galaxy. So from galaxies, we think we know how they've grown. This is our nearest neighbor galaxy. It's called the Andromeda Nebula because it's in the constellation of Andromeda. And it has two little miniature galaxies orbiting around it, and they're falling in, and they're going to be swallowed up in this kind of collision process. So we think our own galaxy was made in a way similar. We even have two miniature galaxies orbiting around our own galaxy, the Milky Way, and they're also falling in over the next few billion years. So we think we have a general idea of how this happened from the earliest materials. Then we'd like to know how stars are born inside the galaxies, and we think that they're still happening. We know that they're still exploding. So here's a star that recently exploded. It's cast its light out into the universe, and some of it's actually bouncing off of dust clouds that are nearby. So this is a remarkable event that was captured in the picture. So we know stars are born and stars explode, and we think that the sun and our solar system were made out of recycled material from these kinds of explosions, so that we have a story now about how beautiful planets like Saturn could form from that initial material. And then astronomers are still busy and trying to figure out how it could be that a planet could support life. So how come are we here? Well, here's this amazing little tiny creature that lives here with us on the Earth. Well, when biologists figure out how that could happen, maybe they'll also understand how we could happen. But there's a tremendous mystery that is still open after astronomers finish their work of saying, how come is the Earth wet and at the right temperature? So that's the part of the great mystery of life. How is it that we're here? Now, jumping forward many billions of years, see the universe is about 13.7 billion years old. The Earth and the Sun are about 4.5 billion, which is about 1/3 of the total. Creatures like this are pretty recent. Maybe the last 500 million years there have been creatures like this. And people like us, able to look out and consider all of this, are quite recent. So here's Galileo 401 years ago now, in 1609. He pointed his little telescope at the sky and said, guess what? It's not what you all said it was. There are little things orbiting around Jupiter, and he could see the little satellites go. There are 4 of them. You can see them with binoculars yourself. He saw little ears on the side of Saturn, and he didn't know that there were those magnificent rings, but he saw something was up. He got kind of wound up in politics of the day and ended up under house arrest. But he was still a person of great honor in his time, and people may not realize that, but in his time he was also a great hero. And so he's buried in a beautiful church in Florence, right across the hall from Michelangelo, and they have equally beautiful tombs. So anyway, he started off modern astronomy. We will celebrate the International Year of Astronomy in 2009 in honor of that particular event of his telescope. He also even discovered sunspots and mountains on the moon. So a tremendous revolution started for astronomy. Incidentally, there was a tremendous military effect of having a telescope as well. So in fact, that was the reason why the real inventor of the telescope didn't get a patent. People recognized immediately that it was militarily important, and they didn't want the secret to get out. But of course it did. Now, jumping ahead another 350 years to 1958, the United States began the space age, and for itself anyway, in 1958 with formation of NASA. We've had some miraculously wonderful things happen since. This is just an illustration of one of them. But again, NASA was founded in the height of the Cold War against the Soviet Union. So now I want to surprise you with some stories and go into a little more detail about how we got here. So when you look in the mirror in the morning, you are looking at the inside of stars. If you shave or you comb your hair, or you just put on your makeup or whatever, you're dealing with the atoms that were actually created inside stars that have then exploded. In the Big Bang, according to our story, there was hydrogen and helium left after the great explosion and nothing else to speak of. So when you look at carbon, oxygen, nitrogen, sulfur, iron, everything that we're made of, it wasn't there then. It was made inside nuclear reactions inside stars, which then blew up, just like I showed you in that picture. So I don't know if you look in the mirror in the morning and you see your whiskers, you don't say to yourself, exploded stars, but I do sometimes. And you know, it's still a mystery. And it doesn't feel like it. It feels like, oh, I've just got to get to work today. But, you know, there you are looking at the inside of an exploded star. So how did that all happen, and how did we know that? Well, I want to now tell you some of the story of astronomy, how we learned all these things. So the first thing, I have some drawings for you to sort of summarize how we found out. First thing astronomers do is they want to look back in time to see how things used to be. So we use light. Light travels very fast, but not so fast that it doesn't matter. So it travels 1 foot in a billionth of a second. It travels 6 trillion miles in a year, and it's a nice round number. So if you look at things that are far away, you see them as they were when they sent light to us. And so if you look at things far enough away, you see them as they were a very long time ago. The nearest star, you see it as it was about 4 years before. The middle of our galaxy, about 25,000 years ago. If you look at the very farthest away things you could possibly see, it's almost 15 billion years back in time. The modern number is 13.7 billion, because this is an old drawing. So now I want to tell you how did we find out how big stuff is. So we do it the same way the Egyptians and the Greeks learned how to do, with surveying. That's the first method. If we can draw a triangle between 2 places that we're looking from, say here and here, and we know the distance from there to there, and we can measure these angles, then we can calculate the entire size of that triangle, and if we do it very well, we'll get it right. So the ancient Greeks were actually able to measure the size of the Earth by this method, and even approximately the distance to the moon. Some of them knew this answer. Now the distance to the sun was too hard for them. It's too far away for them to measure that angle. But astronomers nowadays, we've been able to do this for billions of stars, and so we know pretty precisely, but it still only works out to relatively short distances. As after a little while, the angles are too small and you can't measure them. So what do we do next? The next story is things that are faint are farther away than things that are close. And we have what astronomers call the inverse square law, that the brightness diminishes as the inverse square of the distance away. So if we have two candles and we think that they're the same, we can calculate the ratio of distances. So this is simple, except it's not. The hard part is to see if those two candles that look similar are really the same. And so astronomers have spent or wasted or whatever many decades trying to figure out whether things that look the same really are. But if we can get it right, then we can make very precise calculations. So the next thing we want to know is, well, how fast is stuff moving? And so some things move across the sky very quickly. Planets do. May orbit the sun every few years, or even in the case of Mercury, every 3 months. The moon goes around us every month. The sun looks like it goes around us every year. But there's only a handful of things that do it fast enough for us to see. So for more distant things, we have the capability of measuring one additional factor, which is the thing coming towards us or going away. And if it's coming towards us, then the light that we receive from it will be a little bluer, shorter wavelengths. And if it's going away from us, it'll be a little redder, longer wavelengths. So we do this by spreading out the light from a star with a prism or a grating. And so we see these little characteristic bars across the spectrum, and each one comes from the effects of a particular atom or molecule or ion in the atmosphere of the star. So what we've seen is that almost everything's going away from us. And so we can measure the distances by the triangle method or the standard candle method, and we can also get the speeds this way with what's called the Doppler shift. So in 1929, Edwin Hubble did this, and he got the first few points on this chart, and he plotted the distances of faraway galaxies in millions of light years in one direction, and the speed that they're going in the other, and they're almost all going away from us except one. And so he got the beginning of this, and right away it was recognized that this meant the whole universe seems to be expanding. So in 1929, he discovered the universe is expanding, and the worldwide economy collapsed. So which was the better news? Anyway, he got a tremendous amount of public recognition for this. It was front page news around the world. It was before sound bites, so people actually read and appreciated these things. And he was a tremendous hero. Now I want to tell you some more stories about this. It wasn't exactly quite right at the time. He had the distances incorrect. The candles that he thought were the same were not the same. So he thought the distances were smaller than they really are. But nevertheless, he said the universe is several billion years old, and everybody was paying attention. So all you do is you divide the distance by the speed, you get a constant number, which is the age of the universe. That's how long it took for that pattern to emerge. So some people are pretty skeptical, but nevertheless, front page news. Now I want to show you the people who thought about it before it was discovered. So let me start with Einstein over here. Everybody knows who he is. He gave us relativity theory, among other things. He said space and time are not what you think. They are actually mixed together according to how you're moving relative to somebody else. That was in 1905. In 1916, he gave us the additional complication that space and time are curved by gravitation. So this was the first time we had a law of gravity that should apply to the whole universe, even if it's infinitely large. Because we had Isaac Newton's theory, but we knew it didn't work right for a very, very large universe. So Einstein had his equations in 1916, and it pretty quickly figured out that he needed to add this particular number, which we call the lambda constant, to his equations to make sure the universe would not be expanding or contracting, because all his friends said, well, everybody can see that the universe isn't changing, so it's got to be steady. So he added this little number to the equations. A few years later, in 1922, this young feller, a Russian, wrote to him and said, well, I've worked with your equations, and you know what they say, the universe might have been pretty different a long time ago. Maybe it was expanding, and I don't see why you had to put in that constant in your equations. So Einstein basically didn't pay much attention. I think he wrote back and said, you're wrong, basically. In 1927, this young fellow over here, Georges Lemaitre, who was a Jesuit scholar and priest in Belgium, was also working on these equations. And he came to the same conclusion that he had, and he had enough nerve to keep after Einstein and kept insisting. He said, I think there was a great primeval explosion. He called it the primeval atom. Einstein again wrote and said, that's foolish, you're a bad scientist. But it was only 2 years after that Hubble made his discovery that I just showed you. And of course Einstein had to apologize, and he said that was his greatest blunder. So a lot of history went into that. Very forceful personalities. So this was in the time when a scientist, Einstein, getting off the boat from Europe could be greeted by 10,000 people in New York. So there was a time when we were even greater heroes than now. So now I want to show you three scientists who were working on this same subject after World War II. George Gamow came to George Washington University from Kiev in Ukraine, and in 1948 he was thinking about the Big Bang. He's an amazingly creative fellow, and he said, well, let's think about what happened to that explosive material. It should have been hot. Where did the heat radiation go? And what about all those chemical elements? What if the Big Bang actually made the carbon and the oxygen and the nitrogen? And I told you earlier that it didn't. But he thought, well, maybe it did. And so he got this young fellow who was a postdoctoral fellow and a graduate student, and they calculated and thought, and they knew now something about nuclear reactions, because they had to think about that a lot for nuclear weapons. So now we had a lot of progress, and they made their calculations. So they still thought, at least at first, that the chemical elements could have been made in the Big Bang, but they also said the heat radiation should still be here, and it should have a temperature of about 5 degrees above absolute zero, 5 Kelvin. So they were right about that part. Now in 1948, this would have been a very difficult measurement to make, and nobody actually tried at the time. Now later on in 1965, this radiation from the Big Bang was discovered, and a Nobel Prize was given for it in 1978 to Penzias and Wilson, who found it. They weren't even looking for it. But I think in 1948 it might have been possible. With the clarity of hindsight, we know what we would have done. It might, you could imagine that people could have tried and succeeded, but they didn't. So it was a wonderful surprise in 1965. Now I want to explain something terrible to you. There is not necessarily a center or an edge of this universe. Almost everyone that comes to my talk says, well, where was the middle? And what does it look like? And the answer is that there wasn't a middle that we know of. And this is one of the reasons why. I've got 3 astronomers here. Each one can do his or her Hubble calculation and say, I find the universe is expanding. They're all going away from me. This one says, divide the distance by the speed. It was an hour ago that we were all together. This astronomer here can make the same calculation and say, well, we were all together an hour ago. I agree with you. But I think I'm in the middle. So, you know, there's no grass in space. They can't tell who's moving. So conclusion from this is there is not necessarily any center. So, of course, astronomers have been looking to see if there's a center, and we never found one. As far as we can tell, every direction in the sky is pretty near the same as every other direction if you look far away. So pretty random pepper out there, very random pattern, and no sign that there's a center or an edge. No sign that the universe is spinning, no sign that there's an equator, and no sign even that there's that if you could look farther you would see past all the stuff. So maybe there is, but we can't see it. So this is a terrible disappointment for people. We cannot draw you a picture of what it looked like. All we can say is there was a Big Bang, and if I had proper sound effects it would be very loud. But now I want to tell you how did we get here. But first, astronomers will say the whole universe that we can see today, 13.7 billion light years in every direction, at one time could fit inside the volume of a golf ball. So how could that possibly be? Let me explain something. Atoms are almost empty. The universe is almost empty. If you try to take a trip to the nearest star, it's zillions of light years. It's 40 light years away, and it'll take us forever to get there. The universe is almost empty. Even atoms are almost empty. If you were to take the atom and expand it to the size of the whole Earth, then the atomic nucleus in the middle, where almost all the mass is located, would be only as big as 2 Goodyear blimps. So atoms are empty. So even if you squeeze tight on an atomic nucleus, atomic nuclei are almost empty too. So they're tiny point-like particles inside, and they swirl around. So just imagine that the entire universe was run backwards until stars would touch, the atoms would touch, the atomic nuclei would touch. Everything gets hotter, everything goes faster, but it's really, according to astronomers, we could really put the entire thing into a tiny volume of a golf ball. So, well, that's pretty hard to think about. But now the hard question is, maybe, how come we're here? If it's all flying apart, why isn't it still flying apart? And so here's our story. There are some parts of the universe that were a little more dense than others, and the self-gravitation of the material in those small volumes was able to say, well, okay, I've just got enough gravity to stop the expansion near me. And so some small pieces would stop expanding. So the denser one would stop expanding sooner and collapse to form maybe the first star. And then a slightly less dense region would take a little longer to collapse, and eventually it'd form a star also. So after stars form, of course, then we can have nuclear reactions. And stars like the sun can burn and produce chemical elements, and we can be here. So it's because some small regions of this Big Bang must have been a little more dense than others that we can exist. So how would we know how much stuff is in the universe? Well, for many generations of astronomers have been saying, well, let's see how the universe stops expanding. It must be slowing down because of all the gravitational forces of the galaxies pulling back on each other. So I've got a drawing here that illustrates that. Here are all these attractive forces between the galaxies. So for about 60 or so years, astronomers believed that this was the right picture. And they said, okay, we'll just find out how fast is the expansion slowing down. We'll calculate how much matter that takes, and then we'll know the density of the universe. Well, there was a surprise coming, which I'll come to later. Now let me show you how we think galaxies might have formed. Now we can do the same kind of calculations that the weathermen do with the air on the Earth. We say we think we know where all the stuff is yesterday. We think we know how fast it's moving. We think we know how it does stuff. So let's put it all into a computer simulation. So here is a box of primordial material. Imagine that you could take a perspective so it wasn't expanding. So what we see here is the primordial material flowing together under its own gravitation to make galaxies. That's what these little speckles are on the picture. So maybe it was like that, maybe it wasn't, but it would be a good thing to check this out. So many generations of astronomers have been trying to see if this is the right picture. So that's the sort of basic scientific background. Now I want to tell you about some of my life in this subject. In 1974, I finished graduate school, having tried to make a measurement of this cosmic microwave background radiation. And this is 5 years after the Apollo launch that went to the moon. So NASA was now soliciting proposals for scientific satellites. So I told my my advisor, well, you know, my thesis project was really hard, and I'm really tired of working on that subject, but it would have been better if we could have done it in space instead of hanging our apparatus on a balloon. And so he said, well, call up your friends. Here's a list of people to call, make a team, propose the satellite. It was called the Cosmic Background Explorer Satellite in 1974. Well, we didn't really expect that it would be chosen, but out of the 150 proposals that were submitted, about 10 or 12 were actually chosen, and ours was one of them. So this thing which we sketched in the days before computers could draw That is about what it looked like in 1974. After a long process, we built something that looked a lot like that, and this is what it looked like in 1989, the artist's view of it. This satellite is still up there. It's called the Cosmic Background Explorer. It's about 560 miles above the Earth and orbits around every 103 minutes. And it's in an orbit so that the sun always shines on the side and the Earth is always underneath. So this instrument package up here is always protected. So that's real important because the thing we're trying to find is really faint and the Earth is really bright. So we've got to protect the instrument package. So there's a tank of liquid helium up there in the top to protect two of the instruments, and there's this conical shield around them which protects everything very well. So in 1982 we got approved to build this at Goddard Space Flight Center using in-house engineering teams. And we were building right along, and in 1986 the Space Shuttle Challenger blew up on launch. We were going to use one of the space shuttles to carry this satellite into orbit, and we had a different design. So we had to change the design and rebuild the entire apparatus to go up on an old-fashioned expendable Delta rocket. So this is the way that it finally looked. But it took us only a little over 3 years to finish that complete redesign, and it was launched in 1989. And so within a few weeks of it, we had a major scientific result, which I'm about to show you. And here is this is my thesis project made bigger and better. And so what it's called is the Far Infrared Absolute Spectrophotometer. And the purpose of it is to find out if the Big Bang radiation that's coming to us has the right spectrum. And the spectrum is how bright is the radiation at each different wavelength. So there's a particular theoretical curve that it should follow. And so the main point here was that we could take our little thing, we call it a movable black calibrator, but this is supposed to emit exactly the same kind of radiation that the Big Bang would have given us. So if we measure the sky, and then we put this apparatus, this calibrator body in there in place of the sky, and we get the same answer, then we've confirmed that the Big Bang theory is correct. So that's what we did. I made it sound simple, but it isn't. This is a design of an apparatus which we trace back to Albert Michelson, who was the first American scientist to win a Nobel Prize. And he basically invented this whole technique of dividing light and having it interfere with itself and come back to be analyzed. So without going into the details of how it's done, let me just show you the answer that we got. And here is the theoretical curve. The smooth curve is a theory, and the measurements are the little boxes that are right on the curve. So this is based on only 9 minutes of data that we had taken early in the first few weeks of operation, and we already could tell that our basic objective had been met. The Big Bang theory is correct because the little boxes are all on the curve. And so this particular curve got us a standing ovation, and it was quite a surprise to me. I thought, well, everybody knows that's the right answer, but everybody did not know that it was the right answer. We had many measurements that had been taken, including with my thesis apparatus, that had given misleading or wrong answers. And we had many bizarre kinds of theories that would say, well, the Big Bang isn't correct, something else is going on. And so not only is it a nice curve that looks pretty to look at and fits people's wishes about what the Big Bang should be like, it actually is a tremendous relief. Because before this we had some really bad theories, and there was even a competing very ingenious theory called the steady state theory that said it's only the universe is fooling us, it only looks like it came from an explosion. It's been here for zillions of years and it keeps replenishing itself. And matter is being created to replace what seems to be stretched out. So that whole theory could never explain this curve. So that was a big point and a tremendous end of discussion. So now this curve is in textbooks every place. So we even now have the exact measurement of the temperature. This is 2.725 degrees above absolute zero. And I should tell you that the radiation is pretty bright. If you were to tune your TV to channel in between channels where there's no signal, and you see this snowy pattern on the screen, about 1% of those little snowflakes on the screen come from this radiation. So it's pretty bright. There's a lot of it. It's just hard to measure. So now I want to show you the second scientific apparatus that made cosmological discoveries with this observatory. This is a sketch of the microwave radiometers. And this is a device which is designed to say whether the sky is the same brightness in every direction. So we have two antennas on here, and they point in two different directions. And we have a little switch here which oscillates back and forth between the two directions. So if the output of the receiver changes when you move the switch, then you say the two directions were not equally bright. So we made lots of these. We made hundreds of millions of measurements in this way, and we put them all into a giant computer program, and we made maps of the sky. So now I'll show you these maps. And before I explain to you what we saw, let me say that Stephen Hawking looked at these and he said this was the discovery of the century, if not of all time. So why would he say that? Well, now I have to tell you what it is. The top map is a map of the entire sky, and the middle of our galaxy is right in the middle. And this is the direction of the constellation Leo up here where it's pink. And so what we found is that the Big Bang radiation is not equally bright in every direction, but it's a little brighter over in that direction because as it happens, we're moving towards that constellation of Leo. And so the rain is coming, hitting us more on our faces than on our behinds, so it's a little more intense in that direction. So we have to explain that velocity eventually, but we knew there would be some kind of speed. So we said, okay, well, account for that, subtract that, and we got this map. Now, this is a map of the sky, but there's also this red blob across the middle, which is the place we live. It's the Milky Way galaxy. And we said, well, we knew that we lived in the Milky Way galaxy. Subtract that as well. And now we have this map of the whole sky, and we have pink and blue blobs where we think we've gotten rid of everything that's local. So these pink and blue blobs are the map of the beginning of the universe. And the cold regions, as it turns out, are the dense ones. Those are the regions that are going to grow up to be us, to become galaxies, stars, groups of galaxies. And the warm regions are going to grow up to be empty because all the material will fall towards the dense regions. So that's why Stephen Hawking could say this was such an important discovery. This explains how come we're here. So this was a hard measurement. These are really, really faint, but very, very important. So it took a few years, but in 2006, the Nobel Foundation announced that George Smoot and I were receiving the Nobel Prize in physics. And this is what they said it was for our discovery of the black body form, which is that curve with the little boxes on it, and the anisotropy. Anisotropy is Greek. That means it's not the same in every direction. And that's the pink and blue blobs on that map I just showed you of the cosmic microwave background radiation. So it wasn't the first time the Nobel Prize had been given for this radiation, because it's just the discovery got a Nobel Prize in 1978. But it's pretty important. So now I want to go on and say, well, it really happened. There's me with King of Sweden. I got my diploma and my medal, and a nice check which I've sent to a foundation to give scholarships. So then I want to show you what happened after that. Now, I want to come back to the story of the universe. Here is a better picture than the one that Kobe could do. This was made by the Wilkinson Microwave Anisotropy Probe, which was put together by Goddard Space Flight Center along with people at Princeton, and members of the Cosmic Background Explorer team did this. So this is just a much better map, and confirms everything that Kobe discovered, but does better. So it also confirms some very strange things, which I'll tell you about. Here's a cartoon from the New Yorker. And the caption at the bottom says, "Scientists confirm today that everything we know about the structure of the universe is wrong. And so that's happened quite a lot in astronomy. And now I'll show you what we found out that changed everything. In 1998, it was discovered by using pictures from the Hubble Space Telescope that the universe is actually accelerating. It's going faster and faster. So all this gravity that's supposed to slow down the expansion is not working enough. So that was discovered through pictures taken with the Hubble and confirmed by the details of those little speckles on the map I just showed you. So we've called this the dark energy that's making the universe accelerate. We call it the dark energy because we don't have a clue what it is. Or maybe I should say we have many clues, but none of them seem quite right. And we've got hundreds of theories and only a little bit of information. Another thing that turns up here is called cold dark matter. Well, we look out and we see atoms and we see, well, isn't that all there is? And we have thought that for a long time, but astronomers say different. We say that our kind of atoms are 4% of all the stuff in the universe, and there's another 23% that is called cold dark matter. And it has gravity and is able to affect the ways that galaxies orbit, and that stars orbit in galaxies, even the way that light bends as it goes through space. But we can't see it. All we can do is calculate that it's there. And then there's this mysterious dark energy. So here we are, astronomers, studying the only things we can see, which is the atoms, but telling you that we're missing 96% of everything, and there's a little bit of a mystery here. So when people do figure it out, obviously some more Nobel Prizes are at stake. This one might be the next one to yield. It's just possible that we will discover in a laboratory some particle of this material, and then we'll be able to say, we're beginning to understand. And the people that are looking say that this could happen in the next few decades. On the other hand, maybe nature's not cooperating with our opinion, and maybe we'll never see it. But we're quite sure this is there. So now I want to move on to my current project, which is called the James Webb Space Telescope, which is the planned successor for the Hubble Space Telescope. And why would we need another one? Well, Hubble telescope is a fabulous, beautiful telescope and takes magnificent pictures, but it doesn't see all the way to the edge of the universe. It doesn't see as far as we would like to see. So one reason is that it doesn't measure infrared light as well as we would want to. So what's special about infrared light? Well, infrared light comes from people like us. Here is a floor where somebody's been standing, and if you take a picture with visible light, you don't see any sign that a person has just been standing there making the floor warm, where his footprints or her footprints have been. So you can measure with infrared all kinds of things that you couldn't tell. Similarly, with a coffee cup, you can tell about the circulation of the coffee, you can tell how warm it is. Amazing things to be learned from infrared light. Now, for the study of the distant universe, it's important to us because the expanding universe stretches out the light that we get from distant places because of this Doppler shift. So if we want to see as far away as we think we can, we need to measure infrared radiation. So that leads us then to build a big telescope that can observe infrared. So here's a picture of it. And so it doesn't look like your standard ordinary telescope. It looks more like a solar energy collector in the desert for a lot of reasons. But now let me tell you what happens. Starlight comes from the distant sky, bounces off this parabolic mirror, which is made out of 18 pieces of polished beryllium. And then it's focused in on this little mirror here and bounces down into the instrument package here. And before I tell you more about it, I should say, who is James Webb? Well, there's a James Webb who's a politician now, but it's not the same one. Our James Webb was the second administrator of NASA, and he organized NASA to go to the moon. He built up NASA into its modern shape back in the 1960s when I was a kid. And he not only got us to the moon by organizing NASA in this way, he said science is very important. And he argued with Mr. Kennedy that this was not just a publicity stunt. This is not just proving we're better than the Russians. This should have a long-term impact for science in the United States and for the world, and it was going to be the lasting legacy of that project. And he was right. We owe quite a lot of the scientific enterprise of modern times to him personally. So now let me tell you more about the telescope. It is being built by a contractor, Northrop Grumman Space Technologies, located near Los Angeles Airport. It is being managed by Goddard Space Flight Center here, and we are in partnership with other parts of NASA, with the Space Telescope Science Institute in Baltimore, and with the European and Canadian space agencies that are contributing pieces of this observatory. So it's to go up in 2013, which is not so far away, and it will observe the most distant universe. So the telescope, I should say, is also enormous. This telescope is about 2.5 times as big as the Hubble Space Telescope across the mirror. That mirror, this collection of 18 hexagons, is 21 feet across. It's huge. And so we need that in order to see the most distant and most faint objects. Now I'll show you where it goes. It's going into orbit around the Sun and Earth at the same time. There's a number of places that move around the Sun with the Earth. They're called Lagrange points. So here's one. It's 1,000,000 miles out farther from the Sun than we are. Here we are. There's the Lagrange point. So it's going to go out there. It's 1,000,000 miles from us. And that does, of course, mean that we can't get there to service this observatory the way that we have for Hubble. So it means we have to get it right. I want to show you how big is this observatory in a sort of more tangible way. Here is a team at Goddard Space Flight Center of about a couple of hundred engineers and scientists working on it. This is a full-scale mock-up, not exactly the way it's going to be built, but shows you how big it is. And there are about 10 times as many people as this elsewhere in the world building this observatory. And that's about what it takes to build great observatories. It's similar to what it took to build the Hubble Space Telescope. But it's a lot smaller than what it took to go to the moon. 500,000 people worked on the Apollo project. So now I want to show you how it folds up. The telescope is much bigger than the rocket, so it has to be an origami kind of telescope. It's very carefully folded to fit inside the top of the rocket. It will unfold after the launch, and here is a movie of how it will unfold. First comes out the solar panels and the antenna to talk back to the Earth. Then the protective sun shield pops out. Then the shield will continue to come out. Here we see it stretching out. Then after that's completed, then the telescope will pop into shape. And this movie of it is going about 10,000 times faster than the real thing. Obviously, we'll be very cautious about this because we can't fix it if we goof. So now you're about to see it rotate around. The rest of the telescope will pop out, and then it'll be finished. This is all happening while it's making its trip to the Lagrange point. It takes a couple of months to get all the way out there. So now finally the telescope will pop into shape. So there it is. Okay, well, we're coming along quite well with the assembly. Here is a test mirror that we've made. You can see it's shiny, and you can see how big it is. Now, an individual human being can actually lift one of these pieces of the mirror. So this is a tremendous technology improvement that we've made. It used to be there was no way you could come close to that. It would take 10 people to lift that in the old way of doing this. We have learned how to make an adjustment. All these 18 pieces will not be in the right place when we launch. So we've made a scale model telescope, and we've learned how to adjust them using the mathematics that we got when we had to fix the Hubble Space Telescope. Now I want to illustrate a few of the scientific points that we'll be pursuing. Here's a computer movie of how two galaxies would collide. So that's how they would look. Now we have a picture. This is a real photograph from Hubble of how two galaxies do look. And now we're going to show you how they might continue to evolve and what will happen to them. The two of them merge, this most amazing collection in this collision. And I have to tell you, this might happen to us. In about 1 billion years, the Earth will become too warm to live on because the sun will get brighter. In about 5 billion years, the Andromeda Nebula, that beautiful one that I showed you with the 2 satellites, it's coming at us, and it's going to get us. So what's going to happen? The stars actually don't usually bump into each other, but they start to orbit differently. So our sun could go into orbit around the Andromeda Nebula. Then after 7.6 billion years, the sun will actually swell up to be so large that it'll include the Earth in its inside. We'll actually be inside the sun at that time, and it'll be too warm to live here. So maybe we will have developed space travel. Maybe not. At any rate, it'll be different then. So that's one thing we want to learn about with the new telescope, because we don't get to watch the movie, but we get to see lots of snapshots of galaxies doing their thing, and hope to understand this process. We will take pictures like this one, which was taken with the Hubble. It took 2 weeks to get this picture with the Hubble Space Telescope. And the things that we're actually looking for now that would be at the very most remote parts of the universe aren't even in this picture. So we need a bigger telescope that can observe infrared to see farther away. And almost everything in this picture is a galaxy. Galaxies are very, very numerous out there. So closer to home, we want to see how stars are born, how our own star is born. Here is a place called the Eagle Nebula, where stars have just recently been made. And you see these huge clouds of dust that are blocking our view. That's some of that recycled material that from previous generations is actually solid dust grains in space, and we can't see past them. But if you use infrared radiation, you can see past the dust grains, and we have a picture from the ground that shows the same place from the ground with infrared. You can begin to see through the dust clouds and see how stars were made. Here's one that you couldn't even see before because it was completely blocked by the dust. So this is one of the things we want to do, is to see how stars are being made. There are places that the Hubble telescope discovered in the constellation of Orion where the brand new stars have been made, and they're visible as silhouettes against the background. So plenty of places to look to see new stars, and maybe even inside these clouds might be signs of planets that are in there with them. So we have a movie that shows you how planets might have formed. This is an artist's concept, not a real thing, obviously. But here the picture is that there's a cloud of little rocks orbiting around the sun. And you see the little rocks passing each other. And eventually we imagine these little rocks, however they were made, they will start to stick together to make planets. So here come the little rocks. Maybe it was like that. But we sure would like to know. Well, we can study some places outside the solar system where this is currently happening. And we can study our own solar system as well. But in the outer solar and around another star, this is a place called Fomalhaut. It's a very bright star in the southern sky. It's the brightest star in the southern Fish constellation. And so we found this star that has a ring of dust orbiting around it. We've seen it with both the Hubble telescope and the Spitzer Space Telescope. And the amazing thing is this ring of dust is not even centered on the star. So why would that be? One possible good reason is there's a planet that's pulling the dust grains away from the middle. And we can calculate where it is and how big it is and how bright it is. And we calculate that we should be able to see it with our new telescope. There is another way that we have to look for planets. Once in a while a planet will go between us and its home star. So we have a movie of a remarkable thing. This is the moon going in front of our home star. And it doesn't usually look like that from here on Earth. This is a picture taken with a NASA observatory in space, a little farther away. Anyway, this is the real sun, seen with an observatory called the Stereo. And so we were very lucky to see that. Now, here's an animation of what it might be like for a more distant star, a very more slow motion sort of thing. This little planet's going across its distant star. It would typically take about 6 hours to do this. What we will see is that the distant star gets a little fainter for a little while because this planet is blocking some of the light. And we'll also see that some of the light from the star is going through the atmosphere of the planet. So we get to study the chemistry of the atmosphere of that planet. So if the planet were alive and had certain things in it, we would be very fascinated to know that. Now maybe we will, maybe we won't be able to do it this time, but it's definitely a powerful technique. And there's an observatory which will be launched next year called the Kepler, which should observe maybe 5, maybe 50 Earth-like planets doing this in front of other stars, and hundreds or thousands of bigger planets doing it. So we've got lots of targets to follow up for this method. So there's a chance, even by this method, to see if those planets themselves have moons. It's quite an astonishing, powerful technique, which is already being used today. We already know, for instance, that there is one star whose planet has methane in the atmosphere, and there's a sign of water and a sign of sand grains or silica dust in one of these. So that's one thing to do. Once in a while, we get the opposite effect happens. Here is an artist's concept of a planet. It's going to go behind its star. So here now, if the planet goes behind its star, the light will also get a little bit fainter because the star is blocking the light from the planet. So if we can measure this, and we have already with the Spitzer Space Telescope, we can begin to learn about the planet. So we've even been able to calculate something about the wind on one of these planets because of the way the temperature of the planet changes as it goes around the star. So very, very powerful technique to look for things about planets around other stars. Now, one of the great missions of astronomy in general seems to be, are we alone? Are we the only living things in the universe? And so where would we look? Well, clearly planets around other stars are a place to look, but there are some places that are closer to home. And I'll show you a picture of one that Galileo discovered. This is called Europa. It's one of the 4 moons of Jupiter that he discovered. And 2 or maybe 3 of those moons have an ocean covered with ice. So here you see the surface of this moon, and you see the white color, the ice, and you see also these sort of mud-colored cracks between the pieces of ice. So you would say, well, why don't we go look and see if that ocean's alive? Now, if we land on the surface, we're pretty sure that what's on the surface is not alive, because this is a very hostile place to live. But on the other hand, if you could learn how to analyze the, the components of the mud that's coming up, or alternatively to drill through the ice with something, maybe you could learn something more complete about it. Maybe it's alive. So there are 2 chances there, as well as everybody knows that Mars was wet and could have been alive. Now we know in the last few months, we know that 2 satellites of Saturn could also possibly be alive, because the satellite Titan, which we sent a probe to land on the surface, and we've mapped the surface many times. We've seen that the surface, which we think is covered with ice, has actually been changing its shape. Ice has been moving over the last 6 years or so since we've been measuring. So conclusion is that it's floating on something liquid underneath, like water, ocean. So Titan might be wet and alive. And even more strangely, there's a small moon of Saturn which has geysers, water geysers, that are spritzing out hot water. And so we'll say, what's underneath that? Well, could that be alive? It's a pretty unlikely place that's to be alive, but nevertheless, 4 places in the solar system besides Earth and Mars that are wet, and maybe it could be alive. So that's certainly a place to go look. Now, coming back to the looking for life around on planets around other stars, we clearly need a bigger telescope than even the James Webb Telescope to really find out. So this is one way that people have, and this is quite difficult, but this is basically pursuing Albert Michelson's technique, the same guy that got the Nobel Prize in 1907, combine light from this distant star from several different telescopes, collect in many places, and beam it all over here to this 5th place and make an image. Maybe you can see the light from the planet. So maybe this will be the way we do it, maybe some other way, but in the next few decades we could do this. So what would we look for? What we are looking for as signs of life is illustrated here. If you could find a planet where there were these 3 chemical compounds in the atmosphere, you would say it's alive. What's here? Water, need water. Carbon dioxide, sort of basic, but here's this one special, ozone. Ozone or oxygen. Our planet has ozone and oxygen because of photosynthesis. And so if we found a planet where there was this combination, we would say, you know, not only is it alive, it's got photosynthesis. So maybe it's like here. Now, maybe it's not like here. Maybe we would not find this pattern, and it doesn't mean it's not alive. But this is an objective. If we could find an Earth-like planet, it would probably do this. So that's one of the great hopes of astronomy. So I'm going to wrap up and tell you that there's some things I cannot answer. Here's some questions I cannot answer. But maybe you all will help us answer these things by and by, or especially the students may get to answer these, because these are hard questions. But anyway, I would welcome questions from you, and maybe some easier questions. Thanks. Question. Okay. Have we got a microphone for you? Just a second.
All right, you said there's no center and no edge, but then when you say we're looking at the edge, you just mean further out.
Yeah, I mean as far as we can see.
Okay.
When I say edge.
You just said there was no edge.
Yeah, we think there's no edge, but there's a limit to how far we can see, and so there's a kind of observable edge. Yeah. And that, okay, here's a question.
How did the Nobel Prize change your life?
How did the Nobel Prize change my life? Well, I must say I've been very much in demand as a public speaker ever since. And I like to tell the story of the universe. And so also it's, well, it's a little confusing because there's so many new opportunities of what to do. But that's the main thing, is more public speaking. But mostly I just want to work on this new telescope, the James Webb Telescope, and get that really to go, because that's the next big thing for astronomers. More questions?
Thank you for your talk here. One thing I didn't see in here, I didn't see the Bible and God. Can you address that as part of your beliefs and your stories?
Well, I'll say a little bit about that. I'd say if Moses had come down from the mountain with this story, nobody would have believed him. So we've learned a little bit since then. I personally look at this and say our job as scientists is to find out what has happened. How does it work? And I think the explanations of how it all got started, that's way beyond us, and what it means for the human spirit, even what is the human spirit, that's not something scientists can really tackle. We're just telling you what we found. And I think that's our job. But it's a magnificent story.
That's a good answer. Thank you.
Yeah, so more questions?
As a scientist for NASA, you've made tremendous contributions to the scientific community. What challenges do you face within the NASA community when you're working with engineers who are building the instruments that calibrate the measurements and the theories that you have, and the program managers who are trying to keep things within budgets and schedules? How do you and your colleagues kind of put that all together and have as many successful missions as you've had?
Well, good question. It seems to me that one of the skills that is underappreciated in the world is project management. That the idea of the scientist that he can write down in a paragraph or a page or a small book, to translate that into the work of 2,000 people for 5 or 10 years, that's way beyond any scientist's ability to describe. And it's, I think, a tribute to the organizational talent of our modern society and to particular individuals in our system. And to me, the managers that make this happen are heroes. So that's part of my answer. Another challenge, of course, that we have is that what we think of is always much more expensive than what we wish it would cost. But I think that's part of life, right? Ice cream's more expensive than we want also. So we have somehow to chart a course through life and make choices that produce discoveries frequently, and not only to choose the big missions, but also to make small ones. Both are very important for progress. More questions? Question?
Do you have, what is your speculation? I'm sorry. What's your general speculation as to what the dark matter or the dark energy might be? Do you have any other guesses?
So what could the dark matter or dark energy be? The particle physicists, the people who've been crashing particles into each other in great accelerators and trying to understand the huge multiplicity of elementary particles, they have a place in their theory for these kinds of stuff, especially for the dark matter. They have invented things called partner particles or supersymmetry. So there's a whole array of potentially invisible particles that would have gravity but not do anything else. So they've got a story, and right now we haven't got a proof. But the fact that this dark matter exists is real important to them. The dark energy is also predicted now by many theories, but we have many more theories than we have measurements. And so we can't tell if any of them are correct. Similarly, we can't tell if there were other universes. Many of the calculations say, well, what if there were other universes that happened along with ours? Would we ever know? Well, probably we would never know, because they're not somehow closely enough connected. So people are looking, and once in a while we get lucky and we find a way. When the theory of inflation, that's our story now for the earliest moments of the universe that we're in, was first invented, a lot of people were skeptical, including myself. But now it seems that we have tested it, and it's passed the test. So that wasn't something I expected, but the little speckle patterns of the Wilkinson Microwave Anisotropy Probe map, that big map with all little speckles, that can be analyzed very carefully to say, yeah, the inflationary theory could be right. And that was a surprise to me. And there are more things coming. So we have much yet to learn. More questions?
You may have said it and I missed it. What exactly is the inflational theory?
Oh, I didn't really describe the inflation theory, but Alan Guth suggests and this has now been worked out by many people, that the first sub-microsecond of the universe included a time when the universe doubled in size at least 100 times, very, very rapidly, all in the first microsecond. And we call this the inflationary period because we use the same term for economics, of exponential growth. Why did it happen? We don't know. But we have mathematical descriptions that fit what we see. And so that's kind of a surprise of modern times.
So that's part of what happened before the Big Bang?
It could be. Or it's the first part of the Big Bang. Okay, I think we've come to the end of our tape. So I think we conclude our talk, but I'd be very happy to talk with individuals. And also I wanted to thank the technical team. I think there are altogether 7 of us, including me today, to make one of these events happen. So thanks.
Thank you.